Hi, my name is Brian Caffo, and this is a lecture on regression to the mean in the Regression Coursera class. This is co-taught with my collaborators Jeff Leake and Roger Peng, and we're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. So, regression to the mean is a historically very famous idea, and it basically answers the following question, or kind of answers the following question, let's say. Why is it children of very tall parents tend to be tall, but maybe not so tall as their parents? And why is it that children of very short parents tend to be short, but maybe not so short as their parents? And let's assume when we're discussing this, both parents are tall or both parents are short, just to avoid the discussion of or maybe the average height of the parents is tall and the average height of the parents is very short, and so on. Paradoxically, when we look at it the reverse way, the same is true. Why do parents of very short children tend to be short, but not quite as short as their child? And the same thing is parents of very tall children tend to be very tall, but maybe not quite as tall as their children. And you know, this idea tends to pop up quite a bit. Why do the best performing athletes this year tend to do a little worse the following year? Almost always. And that's a famous idea, and it's called regression to the mean. So anyway, it was invented by Francis Galton in his paper, Regression Toward Mediocrity in Hereditary Stature. Here's, I give the exact citation, it was in 1886. So here's the way to think about this. Imagine if you just simulated random Gaussian variables. Then the largest one, the largest first ones would just be the largest by chance. And the probability that it's smaller for the second simulation is quite high, right? So, you know, let's say I simulate a lot of normals and I take one that's 3, right? 3 is pretty large for a standard normal. Then if I were to simulate another one that was going to be its paired measurement, the chance that it's lower than 3 is quite high. In fact, it's 99% that it's going to be lower. Or in other words, the probability y is less than x given x gets bigger as x heads towards very large values. Similarly, the probability y greater than x is given x equals x gets bigger as x heads to very small values. So you might say when you're talking about, let's say, sport athletes, when we're talking about performance in a sport, there's maybe two components. There is this randomness, this element that's not under their control, and then there's this part that maybe the very best athletes are better because they're intrinsically better, or they trained harder or whatever, but they happen to be better at whatever sport it is they're playing. So there's this intrinsic part, and let's just think of maybe for the purposes right now that the regression line is the intrinsic part. And if that correlation isn't perfect, then there's that leftover random part, and the random part is the component that derives the regression to the mean. So you can think in terms of an athlete, their performance in a given year is part their ability. Some baseball players are just better at batting than other baseball players. But if they're a little bit lucky as well and have a great year, then the chance that they're going to be a little bit worse the next year is high. Okay. And so let's investigate this in terms of heights. Suppose we normalize x, child's height, and y, the parent's height, so that they both have mean 0 and variance 1. So let's get rid of the kind of difference in the spreads between the two variables and shift differences. Then recall our regression line passes through the origin. That's in this case the mean of the x and y's. And then recall the slope of the regression line was correlation x and y times the ratio of the standard deviations, but because we've normalized them, then the ratio of the standard deviation is always 1, right? So the slope of the regression line in this case would be exactly the correlation. So notice if x is the outcome, and there is this thing where if you switch just the plot itself, where in the case where x is the outcome, but you plot it where it's on the horizontal axis instead of the vertical axis, then the slope of this line will be 1 over the correlation. Okay, so let's do that. Let's do that plot. Okay, so I'm using R. Let me get my pen here so I can go through the code. Okay, this guy right here. Let me get it better. Using R loads the library that we need to get this data. The data, in this case, I'm doing the fathers and the sons. Maybe it's a little bit easier to think about instead of having the pair of parents' heights like in the other data set. Okay, and these two lines just normalize the data, so they're both mean 0, variance 1 after this, and then the row is the correlation. And then here's my plot. I don't know why I created a new plotting function for this. I think at one point I was going to use the manipulate function at some point to do it. But at any rate, I created a new plotting function. At any rate, it's going to plot x and y. Here's my x and y labels. I pick my range -3 to +3 because 3 standard deviations below and above the mean is generally encompasses most of the data. This BG equals light blue tells me that the background of the point I want to be light blue and the color equal black tells me that I want the outer outline to be black. PCH equals 21, it just means I want a circle with a line around it. CEX equals 1.1 tells the plot that it wants me to take the normal size of the plotting point and increase it by 10%. Frame equals false just says I don't want the full frame around the plot. I just want the standard axes drawn and not a box. Okay, so that's my plotting function. And okay, so I think the reason I created a new function is so I could fit it all on this next page as well. So here I'm going to plot my x and my y's. AB line is a function that it's a nice generic function, or a nice general function that takes in a slope and intercept and adds a line. But you can also put the fit to linear regression in it, and it'll just add it to the plot. You don't have to actually extract the slope and intercept. Just assign the fit to a variable and dump it into AB line, and it'll extract the two for you. Okay, so this is the identity line. If there were a perfect correlation, that would be the line that you would get. Here's the line where the father predicts the son, right? Because we have son on the vertical axis and father on the horizontal axis, and then son predicts father, right? And then we have to do 1 over rho to account for the fact that the son, which is the predictor, is plotted on the vertical axis, okay? And then the horizontal equals 0 and v equals 0, h equals 0 and v equals 0, tell it to draw a reference line for no relationships. All right, so let's inspect this plot. Okay, let's look at this one more, look at the output of the plot, and here's the identity line right there. So if there were no variation and father's height perfectly predicted son's heights, then that would be the slope of the regression line. And then red. And then if we were to use father's height as the predictor and son's height as the outcome, we would get this line right here. And notice this line has a slope less than 1. Because the correlation isn't perfect, right? The dots are a little bit all over the place. As the dots became less and less correlated, right, this would head down, the red line would head down to 0. In which case you would have 100% regression to the mean. Okay, now let's take a tall father, right, and our regression line would predict that the son's height is right there. What would the identity line predict? If there were perfect correlation, it would predict that the son would be a little bit taller, right? So that difference there is the regression to the mean, right? The idea that the tall father, right? The model is going to predict that his son will be a little bit shorter, as opposed to an identity line. If there were perfect correlation, let's look at a short father, right? So a short father who is 3 standard deviations below the norm for fathers in this data set, right? the predicted height is be right there, right? So still would predict that the sun would be short, but not anywhere near so much as what the identity line would predict, okay? And that distance, that attenuation that's occurred by taking kind of this identity line that would say, oh, well, a tall father, I would predict that the sun would be equally as tall. That change in slope down towards towards a perfectly horizontal line is the regression to the mean effect. And and the regression to the mean is governed by how strong the correlation is. If the correlation is 0, right, this goes all the way down to a horizontal line, meaning we have basically no information to predict, and it's all regression to the mean. If there is 100% correlation, then this would go up to the blue line, okay? And of course, it's just by convenience that we picked the father as the predictor and the child as the outcome. If in fact we had used the son as the predictor and the father as the outcome, we would of course have this same looking type of plot, right? The same looking type of plot, only this would be the prediction line, right? And this is exactly the plot you would get if you were to have just instead have plotted son on the horizontal axis and father on the vertical axis, okay? And notice that this line now takes the identity line, and now is shifting it that direction toward a vertical line in this case, okay? And so just to see that the regression, the regression in the mean effect still is here. Just take a very tall sun that's 3 standard deviations above the norm, right? And go down, right? You get a predicted father's height that's still tall, but not anywhere near 3 standard deviations, right? And there again is the regression to the mean effect, right? Whereas if you went over here, right, that would be that distance is the regression to the mean effect. And again, if the son's and father's heights were completely unrelated, if the points were just a perfect ball, right, then that line would be like that, and the father's height predicting the son's height would be like that, and the son's height predicting the father's height would be exactly like that. Okay. So that's what Galton noticed. And of course, all these lines, by the way, have to go through the point. All the lines, it's nice, they all pivot at the point 0, 0, the mean of the two sets of heights, right? Okay, so let's just discuss this a little bit. If you had to predict a sun's normalized height, it would be this guy right here, from the father's height. And if you had to pick a father's normalized height, it would just be the correlation times the sun's normalized height. So multiply, and then the regression of the mean effect is that multiplication by this correlation shrinks towards 0. That's the regression toward the mean. And if the correlation is 1, then there's no regression to the mean. Father's height perfectly determines child height, and vice versa. And so I would note that regression, this is related to Galton's initial treatment of regression to the mean, but this problem's been thought about quite a bit, and things change a little bit with nonlinear relationships and whatnot, and the nature of the error distribution and so on. So this is a kind of a cursory treatment of the phenomenon, but I hope you get the idea and how it's kind of tied into regression and how you can use regression to sort of think about it. So anyway, it was a very historically famous idea. If you want some interesting reading, you can download Galton's original paper.